How are you? Enzo DiCostanzo, clinical professor of economics and finance, St. Peter's University, Jersey City, New Jersey. This is the last topic for the academic year of 2019-2020. What a year it's been. This is the linear regression and the correlation chapter. This is finally the Excel models. I sent you guys the template this week. You guys had the homework assignment. You had the reading, the pages that you needed to read. You had all that stuff on Blackboard. Okay, and like I said, you guys have been working like this for, since, September, August, September, most of you. So you should be very used to what we're doing. We're discussing that sort of in the school, what are we going to do the year coming up? And my humble opinion is, so again, I'm teaching FN 410 in the fall. I'm teaching statistics and probability, business statistics, probability methods, or whatever it is in the fall. What is it? 300, I think, EC 300. So some of you might be with me again on that. But I think we're going to have some YouTube, even from the beginning. We're going to have a bunch of YouTube classes. So just keep that in mind. I'm teaching corporate finance in the summer. I'm teaching 401 if you guys want to take that with me over the summer. So I think that's what we should do in terms of just getting you guys ready to learn on your own and work on your own. And that's, I want to create out of you guys to be able to work on your own and focus. This morning I watched the documentary on Manhattan Project. If you guys are aware, those were all the top theoretical physicists of the day. They did heavy water experiments to build the atomic bomb that helped America win World War II. Now to you guys, it's a little bit distant because most likely your parents weren't around for World War II. My dad was in World War II, so I remember the story. So I had somebody who had firsthand experience as to what happened in Europe during World War II, and certainly was very devastated 1/6 of the economic area of the world. The European economy, if you take it as a whole, the European economy, France and Germany, all these places, Italy, Spain, Portugal, it's like America. It's as big as much of an impact as the American economy has all by itself. So I was watching a documentary on Teller and Fermi and all names that I knew very well. Not the most engaging people, but the openness that the engineers and scientists, that's what struck me about it this morning, the openness that engineers and scientists have in terms of a conversation compared to business people, where you always kind of looking over your shoulder saying, oh, what's really going on here? How honest is this guy being with me? And what is this guy after, kind of thing, where the scientific community, they're just out to solve a problem. It wasn't the physics, it wasn't the theory, it was if you listen to the guys, Teller and all these different people, the guy from Harvard and the guy from Berkeley, it was building the thing actually. So let's translate that to what we do in our class. It's a nice segue into what we're doing today and what we've done for this whole year. I'm teaching you how to engineer something. The science is there. The science is there. I'm showing you how to engineer sort of what we're doing, how to make a model, and that's what we're going to spend time on today. Okay, so folks, please keep working hard, keep paying attention. You still have a few weeks to go. I know you can't see, I didn't share the screen with you yet, but 1, 2, yeah, a good couple weeks or so. 2 weeks to get everything. So yeah, so folks, please, try not to. I feel like you're waiting. I feel like you're waiting so much with the assignment. A couple assignments due now. You have this last one due. We're not going to have chapter 10. We're not going to have sampling distributions. We're not going to have that. We're just going to have up to correlation. So quantitative data, normal distribution, and the correlation and regression chapter. That's it. So please, folks, email me, send an email. Oh, what are we doing? What are we doing? And I'm saying it in the video. So obviously you got to watch the video to continue to figure out what's going on. Okay. Guys, give me 1 second. Okay, let's share the screen. Okay, folks, so the last chapter that we're going to be dealing with is here, correlation and linear regression. Okay, now for better or worse, again, this is the textbook, page 137. these are a bunch of I think barbecues or something like that that are being sold at the Lowe's. Like is like a Home Depot. There's one in Piscataway near the Rutgers end of Piscataway. There's one down there. I had wished, and if we just looked at, they sell, obviously this is a battery operated drill and all this. I wish that they had given us the data. You see this first graph here, sales versus improvements. This is residential improvements and repairs, sort of, I think nationwide, because it's from the U.S. Census Bureau. So this is nationwide spending on home improvements, and this is this particular sales for the particular retailer. Now, most likely when you add up all these improvements, it's Lowe's, Home Depot, Sherwin-Williams, True Value, the neighborhood stores, if there are any neighborhood stores. If there are, there's some neighborhood hardware stores still around. New Jersey City has them, but it's True Value. It's still True Value, the one on Duncan Ave. I wish that, now, we can go back from 1985 to 2007. I can go to all the 10Ks and get all of Lowe's sales data. I could do all of that, but that's a lot to do for just one problem, and we have other problems with it. Sort of give you the data either on the. I have a disk with the book and all these other type things. That's a lot for one problem. But I wish that I'd looked for it. I looked in the folder that had everything in there, all the data that was in there, the data folder. Where is it? Where is it? I'll look again, but okay. So you have a data. So you have a data for this is all. These are all the data sets here. Do you have something for Lowe's or I don't know? I'll feel bad if it was actually here. Home Depot, price index, occupancy, lobster. Yeah, see, there's no lobster, Lowe's, loyalty, male unemployment, improvements. Maybe it's under. So you have to sort of be a little bit of an investigator with this. I don't see improvements anywhere. Okay. Net sales, maybe under residential. But yeah, so you have to be a little bit of a detective, and again, that's something else I'm trying to teach you guys, to how to find things. But these are all the data sets, okay, and it comes with the textbook. I just sort of downloaded to my hard drive. But I wish that I had these numbers. And here, let me just talk about what this chapter is just generally about. From the beginning here, as a nation, as in the aggregate, in the macro sense, as we spend on home improvements, putting a roof on your house, replacing the doors, putting in central air conditioning, having a electrical generator backup, all the things that I'm working on. By the way, just go through the list in my head because they're at the tips of my fingers and how much it will cost. But and then Home Depot. So me spending how much now? I can tell you, I probably spent as a percentage, probably in Home Depot's chagrin, because the roofing materials we got from another source, not from Home Depot. My guy got the materials from his vendor, which I'm sure was a professional level guy. And see, let me tell you what used to happen 40 years ago when you worked on a house. Home Depot was around, but it wasn't as prevalent as it was today. The contractor had to know the supplier for the doors and the supplier for this and the supplier for that. They had to know all that stuff, and then they sort of advised you. So that was as much of it as anything. What Home Depot did is Home Depot sort of put the power in the citizen's hand, or the customer's hand, to buy the doors and but folks, I gotta tell you, you got to be very careful measuring doors and windows, and is it center line, is it the edge, is it this? Because we had something where we bought a door a couple years ago, and we measured it the wrong way. We measured the door, not the opening, and you have to be, and the door is like 40 years old, so or more. So things were probably measured maybe a little bit differently, in 1985. As opposed to today. But that's basically what this is you're trying to relate. You're trying to say, okay, based on national expenditure on home improvement and repairs, how's Lowe's going to do, how's Home Depot going to do, and all that. That's what this graph is. And we're going to put the math to that. Now, there's two models in the chapter. I'm planning on a multiple part video for regression correlation. I'm planning on a multiple part of that. But we'll do the first one today. But also, we'll dig into the book. But folks, I just want to say ahead of time that I wish I had the data to make the scatter plot and to apply the model that you're going to see. There's one model. So after you see it today, it's a small one, but you'll see pretty much what it is. And here, this is when you're applying this very sophisticated modeling to what's going on in the world. Years, Lowe's net sales, U.S. expenditure on residential improvement and repairs. The units are millions of dollars, the years, in the United States. And what are you trying to do? You're trying to assess low sales relative to the home improvement market. Okay, so that little box with its 6 or 7 points right there, you know 6, yeah, 6. That's it. That you're going through that little box is why you're making this model. Now, there's a lot of detail to what we're going to do, but at the end of the day, you want to, why are you doing what you're doing? That's why you're doing what you're doing. Okay, like I said, folks, I'm going to keep saying, but I really have to apologize for not having the data for this. But we have the equations, the analysis, and we're going to go through all of that. I'm hitting Alt Tab. Yeah. So again, you have this template. This is the assignment template. So now we've sort of transitioned to the assignment Excel versus the in-class Excel, which again, if you're with me in the fall, you probably have to get used to doing that. Again, here's all the topics, ScatterPlots, and this chapter lends itself from the quantitative data chapter, where you're graphing quantitative variables and ScatterPlots, linear model, working variables, causation, the regression and the mean, checking the model, and see this R squared. This R squared is how much of the variability is explained in the model, how much of variability is explained in the residuals. Okay, so is the regression actually this should have been a capital I. It's a small one. Is the regression reasonable? The variation, checking the model, and this we just talked about this from Lowe's. But what's going on with the first example is that if you're looking at a specific home retailer versus expenditure in the nation in terms of home improvement and repairs and things of that nature. You're going to deal with ScatterPlots. You're going to look at the relationship between the quantitative variables. The relationship is often at the heart of what we'd like to learn from the data. That's what you're doing now. When you have and if you look back at the textbook picture here, it's pretty much a straight, maybe not exactly, but it's pretty much a straight line through it. The economy, it goes through a business cycle, even though it's sort of a positive sloping economic output of this nation, but it goes ups and downs, ups and downs, ups and downs. So you need a little more of a complicated model to do that. You need polynomials, you need something else. The sinusoid, the voltage that comes, again, this is way off topic, but the voltage that comes out of the wall is modeled by trigonometric functions. And when I was in physics and in math all the time, I had a little bit more of a handle as to what was going on with that. But I'm sure as I dig into this, we'll see what's going on, what kind of models we're going to use to really model what's happening in the world. Is consumer confidence related to oil prices? What happened to customer satisfaction? Sales increases? Is increasing money spent on advertising related to sales? What's the relationship between stocks sales volume and its price? These are the types of questions that you've got to sort of break up. Oil prices, consumer confidence, customer satisfaction, sales, money spent on advertising, and then Home Depot sales or Lowe's sales or whatever it might be. And the big one at the bottom, the stock volume versus the price. You'll have a lot of people falling over themselves, trying to say, hey, we have an equation that tells what the price is going to be based on the stock volume. And obviously a very valuable thing. Warren Buffett would agree with that. And Trump over the last couple of days, got on Fox Business News and said, "Oh yeah, the economists, what do they know?" The world's a complicated place, folks. And we do the best we can. We have an educated guess. It's not perfect, but we have an educated guess as to what's going on. This is the congestion problem, which I'm not going to necessarily get to initially, but this is. And again, it says, see this. Because I didn't have the data for a lot of this stuff, so I was a little frustrated that I couldn't make these ScatterPlots. This one here, see, it says congestion cost per person and traffic delays. If you're sitting in your car on Bluefield Avenue in Newark or on Route 21 in Newark, you're not working. You could be making business calls, but it's never as convenient to get on the. If I ever make an important business call and I'm in my car, I pull over, put on headphones, shut the car off, shut the radio off. And just seal myself up in there so I can talk to these people reasonably calmly. As you're fighting traffic, the last thing you want to do is, the deal of your life. You're on the phone, sort of screaming at people. That's really the last thing you want to be doing is being on a very important business call. But what's happening here is, as the speed, as you drive faster, the cost per person of you driving your car, which means what you're giving up. Remember the opportunity cost from the fall? What you're giving up to the business can decline because as you're getting from point A to point B quicker, you're getting to your desk faster, you're getting to work quicker. So the faster you can drive around, the less sort of opportunity cost that it is for you to drive to work every day. And folks, let me tell you, look, you guys know me relatively well. Obviously it's a bad thing for the nation, but I was pretty comfortable or at peace with working online and working with videos. I'm pretty much at peace with that. So I feel pretty good about that. And in the fall, believe me, the year coming up is going to be like it is now. The press isn't, you're not hearing because they don't want to cause a panic. You know, the Fox News and CNN, they don't want to create these panics out there. But believe me, it's going to be a year of living like this. So just be emotionally sort of prepared for that. Okay. But with me, you're already working. You were working with video, 8 months ago, or whatever it's 10 months ago. You guys were as ready as could be. I said that in the initial email. So that's what this scatter plot is. So the faster you go, the less opportunity cost, the less cost there is to doing business. But the slower you go, you're sitting in your car. The cars, brakes, stop and go traffic. Where's the car out? You're not getting to work. So there's a lot of costs associated with sitting in traffic, which you really don't want to do too much of that. When I was in college, at NJIT, you would hear things like, oh, you can, even back then, telecommuting was sort of starting, but you'd say, oh yeah, if you want to be a real go-getter, don't just telecommute. But we're in a situation now where I like to think that as a society, we're maybe seeing the advantages of a little bit of peace and quiet and not going bananas out in the world so much, and focusing on your craft, focusing on how you're making money, focusing on what you're doing. Okay, that I hope that's what's happening out in the world and with you guys as much as possible. And don't worry, okay, everything's gonna be fine. Okay, so don't worry, you guys are gonna be okay. So anyway, so scatter plots, what this is, direction of the association, negative or positive, that kind of a thing. So yeah, there's a couple sort of principles here you have to look at. So everyone looks at scatter plots and people find out hard way to say what to look for in scatter plot. What do you see? So right, you want to look at the direction of the association, the form, is it linear, the strength. So it's these three that are the real important pieces to the puzzle. I just call them characteristics or call them the principles of the scatter plots. But the direction, is it positive or negative, and how strong is it? The form, is it linear? Is it nonlinear? Is it polynomial? Is it logarithmic? Is it exponential type things? And then the strength, is there a lot of scatter to it? Those kinds of things. So, and you can see that there were some real quick questions: how much scatter, curved, exotic, straight, positive, negative, neither. Okay, so for again, direction, form, strength. Okay, so you have your general character, and I do it. Being a math guy, I just do it sort of naturally at this point after teaching this material for a very long time. But when you're starting out, you have to stop and think. Okay, direction, association, form, strength. You got to think about that. So all this stuff is in the book. Okay, so like I said, you should at this point, with 2 or 3 weeks to go in the course, you should have read the chapters and all that. Okay, you should have read all that material. Yeah, this is the cyclist example, and here I'll start you on this just to sort of get this sort of off our dish of things. But this actual model, we're going to work on this model at another time. Okay. So yeah, and I just sort of threw these out here, and I'll drop these off in here with you guys. Direction, form, strength. Okay, and escape and copy. Oops. This is your basic data set, and this is something that's near and dear to my heart. Is this bicyclists or is this the guys driving the cars? Yeah, cyclists. Yeah, I'm on my bike all the time. I sent somebody a picture of my bicycle the other day. So yeah, it says there's about 53,000 cyclists have died in traffic since 1932. Okay, I don't know over how. No, I'm not saying look, one person dying is too much, but over 65 years. Something like that. I'm not saying that that's it. One person dying is bad, but over 65 years, if there's 53,000 people, so here equals 53, 1, 2, 3 divided by 65 years. So about 1,000 people a year or thereabouts are dying. Again, that's still too much. 1,000 a year for 60-something years is still too much. But what we did was we put the ages and the years. You can see when the book was written a good decade ago. But I'm still, we can always add to this, and this is not a big deal that it stops at 08 or something. There's really nothing wrong with that. But this is how all those folks work. And as you can see, we're getting healthier as we're getting older, and people dying, we're a little bit, the mean age is a little bit higher as time, rolled onwards, that type of a thing. Yeah, so again, read the book. The book is well written. And yeah, I think we made a plot of this, the mean age or the scatter plot. We did that. Like I said, we're going to pick that up For the next video, which is probably going to be tomorrow or probably tomorrow. But we'll make this plot, show you how to make this plot. But there's a smaller problem that we graph the residuals and all that. But there's a smaller problem. This is a long, there's 10 data points, and you can see all the filling in the after year. I'm going to explain this all, but I'm going to explain it today, but with a different problem. We'll have another video. This will be the centerpiece problem in that video. Yeah, I want to work on the next, and I just saw it over here. So the next, understanding correlation. We're going to work that problem today, that model today. But this is coming, okay, understanding causation, summarizing what the ScatterPlot says. Deaths have been increasing linearly during the period. The trend is a strong trend. I had my accountant's daughter, who was a lot older than I thought she was. Not that she's old, but I thought she was like 20. She's actually like 30. And she'd taken some course online, and she has like trend analysis. And you want to do the math. You want to do the math, okay? And I told her something, and she could sort of bristle at it a little, because I know the mom very well. I was working with the mom for like 20 years. But she bristled. I said, so I don't say her name, but so-and-so. I said, you need to, if you don't know the numbers, you don't know the business. How can you analyze business where you don't know the numbers? She kind of got upset at me. She goes, I want the fast, quick, and easy answer to this. And I said, well, I said, you've got to be able to deal with the math, and we have demand equations, at the end of this chapter. So we did everything we needed to do, but we just did it with a lot of math. Okay, is really what we did. Assigning roles to variables and scatter plots. Descartes had the x and y axis. So again, you being comfortable mathematically, this really tests your math. And again, a lot of this, I'm sort of moving through this, glossing over, but a lot of this stuff is in the book, and you should understand an x-axis, a y-axis. You should understand all that stuff. And folks, again, I really would rather you didn't use a statistical program to solve these problems. I mean, you're going to check your work with a statistical program, that's fine, but I think you should spend the time learning how to do what's in front of you, type thing. You want the relationship between the explanatory variable and the predictor, or the response variable is y. The explanatory variable is the x-axis. So x is independent, you plug it in, and y depends on x, type thing. And there's a lot of different ways to say that mathematically, but that's really what that is. And yeah, it says it right here, explanatory or predictor. The response, see, the response is y, and then the predictor is the x. And I hope I just said that. Yeah, the response is the y, and explanatory predictor is the x-axis. When you make a scatter plot, you can assume those who view it will think so. Can assume those right to view it will think this way. Choose a variable to sign. So yeah, so what you're doing is you're looking and saying, okay, what the response is the vertical, and the horizontal is what we inputted, type thing. How long is your car going to last if you're driving 100 miles an hour everywhere? Not very many years. So as your speed goes up, that's an inverse relationship. So the number of years you're going to have your car goes down as the faster you drive. If you drive in the desert, things of that nature. Like I said, I watched that documentary this morning. They were out, I don't know if you guys are aware of the story, but the atomic weapon that basically won the war for the Allies and America was developed. I think it was New Mexico, because it was not very populated, and they could, I hate to say it, but they set off a nuclear weapon on U.S. soil out in the desert. And I think the closest person, if I remember this correctly, the closest person lived about 10 miles away, and the closest town was maybe 20 or 25 miles away. That's not great. That's pretty close. Think about how far away 10 miles is. And from what this stuff is, folks, a nuclear blast, nuclear bomb is enormously devastating. You're recreating the sun on the surface of the earth is what you're basically doing. And try to control that. It's not it's a fire on steroids is what a nuclear explosion is. Learn your physics. Physics is very, very fascinating. And believe me, these guys, they knew a lot about statistics, and they knew a lot about this stuff. So your learning things are very key to knowledge in the world today. Yeah, independent, dependent. We talked about this already. Y responds to X. Okay, predictor, responder. Yeah. Okay. So you had all that. Yeah, this is the car accidents. This is the correlation. Oops. I should make this a little bit bigger. Yeah, this is the correlation formula. R is what this is. Yeah, folks. Again, always let me know if you can't see things, or if you need to ratchet up the font. Yeah, I want this to be small. These are sort of the answers. I want that to be smaller. Again, when you work on your own, have a nice big screens. Like you can see the screen here is much bigger than what I have it. I don't know if you can see it, but I can see it. It's maybe twice the horizontal distance. But this is the x and the x bar and the standard deviation, and we'll get to how all that was derived. But that's basically the formula for that. This algebra-based course, we don't go through the derivations too much. And you can see graphs and scatter plots. We'll get to that. We'll get to all that. But like I said, that's for the mean. So I want to talk about the Lowe's problem and that one mathematical one. And then tomorrow, or whenever I do the next video, which should be soon, we're going to do the cyclist problem, the cyclist who passed away. And it's basically time. It's basically on time, a time series. Yeah, this is expenditures from improvements, replacements of residents. Okay. Understand the components, United States, the years, measured in dollars, quarterly numbers. Yeah, this now again, we could have probably looked that up too, and I didn't do. We probably could have looked that up. And here's the whole discussion. That's what I basically opened this video with. That as a nation, what do we spend on a nation versus how does that impact how Home Depot does? How does that impact how Lowe's does? How does that impact your true value and all those kinds of things? Is it a linear relationship? Is there some social cycle to it? Again, direction, form, and strength. And that's a part of your homework problems. Well, this week coming up, we'll probably do some video on the homework problems for this particular chapter, so you guys can look at that. But my big fear is that you waited and you waited and you waited for everything, and now you're gonna have this chapter work on this week and next week, and you're still working on something you should have finished long ago. Folks, you got to take responsibility. I love you all, and you guys know that, but you got to take responsibility for what you do. You got to be able to get stuff done. You can't wait and wait and wait. Correlation, we use the letter R for this. That we use that in statistics. We're going to find the z-scores for the x variables. All these problems have to start with a list of data. Okay, these problems all start with a list of data. And yeah, here's the model that we're going to work next, and give us a little bit to sort of get down to it. We're going to talk about lurking variables. We'll talk about all that type of thing. Again, this summation means I'm going to take all my z-scores, add up all the z-scores, and divide by n-1. That's another way to get correlation. But I want you to do it in terms of x's and y's. The z-scores, you computed those, you need another 2 columns. And you can see the z-scores just made from the standard deviation and the data points and the mean. Okay, and you sum the product of the z-scores, which is basically just this. Okay, which basically it's just this thing. Okay, but this is in terms of x. Okay, and like I said, we're not too big with deriving all this stuff in this particular course. It's in the textbook. I think this may have been in the text. You guys can look at it, but just use this correlation function sort of as is for the time being. Okay, and correlation by hand. So yeah, okay. So it's a summation of the product of the data points subtracted from the means divided by n-1, which is degrees of freedom, and then also divided by the product of the standard deviations. Okay, and again, you have this all. And folks, here I'm proud of this. There's a button up here somewhere. Where's that button? Under insert, so go to insert, and then you go to equation, and it gives you all the sort of the options. And you have limits and integrals and summations and script and fractions. See the fractions and the exponentiation, the radicals, the integrals, all those integrals, the large operators, the brackets. Here's the matrices, the different operators. You have all this, and you should, again, if you're going to work in this, you should have some Excel or a software program that, just one spreadsheet program that has the ability. So now I'm a little more sophisticated now with how I can type out my equations. And you can see the Excel, it's running a little bit slower because of this. So that's just something that I noticed. It's running a bit slower, but that's just sort of what happens now. And again, my operating system is still 7, so I got to get up to 10. So in the next year, hopefully, and see, I got delayed a little bit with the people saying, "Oh, what's the impact on me?" I got delayed a bit on dealing with expenses that I had and different things because some of the stuff that I'm going to be working on is delayed a bit into 2021 or something. All of us are sort of facing that. Okay, so like I said, so just take this time as time to work on yourselves, work on your skills. Folks, let me tell you, if you really learn all the stuff I taught you going back to September, a lot of stuff. Okay, so yeah, quantitative variable condition, the linearity condition, the outlier condition. The outliers can distort the correlation, can make another small correlation look bigger. You can calculate correlation for any pair of variables, but the strength of it, you want it to be a line. If it's got all sorts of peaks and valleys, the line isn't going to really, the equation of the line isn't going to characterize all the variability as well if it was just a straight line, even though it was maybe scattered a bit. But all those ups and downs, you need polynomials, you need something else. You need something that's not linear to model that better. Okay, again, only applies to point. Don't use, we didn't cover categorical variables at all, this whole academic year. But in the fall coming up, I might just hit it a bit, in the statistics class. But we spent a lot of time doing this stuff, and I think this is the time that it's worth it to spend the time working on this. But it's got to be quantitative variables, numerically measured, variables, not just yes or no or New Jersey, New York type thing. That's not going to do too much for you. But yeah, so we're going to work this model out right now. Okay, this is the second model, which is here. I just want to go through the math here. It's a small data set, type thing. So I want to hit that. Lurking variables, or we can talk about this a little bit. Lurking variables are, there might be a third variable that's impacting the relationship between two variables that you're initially looking at. It's effect, right, that you've observed. Tall children, reading skills, but then the age could be the lurking variable that you're not accounting for. So there's a lot of forces that go into what's going on, and you've got to sort of be able to sort through what's happening. Okay, that's just something to keep in mind. You've already guessed that the lurking variable is the age of the child. It tends to be taller and stronger reading skills. Okay. This whole life expectancy thing. It could be blood pressure. It's not just men and women and how old they are in the country, but maybe their specific metrics, either the pulse rate or their weight or something along those lines. So there can be other variables in there. And as you understand this more, you'll start to work on multi-factor models where you have all those inputs are okay. This is just to get you started. When you do this for real, you got to put all the inputs in. Okay, so that's something just to keep in mind. Again, the associations and how many TVs you have or whatever it might be. Okay, so there's a lot of other discussion here that you guys can spend a little bit of time with. That's lurking variable. The linear model. Now, again, you're going to see the this is for again, I'm going to keep apologizing the whole way. This is the Lowe's data, which I don't have, but it talks about the relationship, strong positive linear. It has now correlation of 0.97 means 90. Not 97, but 97% squared, whatever 0.97 squared is. That's how much the variations, which is another number like in the 90%. But the correlation just tells you the strength of what the relationship is. How much of the variation is described is the correlation squared and some other things that are involved in it, and we'll get to all that. But the Lowe's problem, there's going to be an equation. And again, years ago, I used to teach the slope here and the equation in the basic course. I sort of got away from it a little bit, but now I sort of went back to it. Here's the equation. See, here it says y hat equals a constant plus a constant times x. This is a linear model. And again, you can see I have this typed out in the nice Excel version of everything. So anytime you see a variable, that little sort of hat, we call it a hat in mathematics. It says it goes up and goes down a bit. It's like an upside down V. Over the variable, that means that's a predicted variable. B0 is a constant, B1 is you can use A and B or B0, B1. X is a variable. And it says we know the model will be perfect. The line we draw, it won't go through many of the points, but the best line might not even hit any of the points. How can it be the best line? We want to find the line that somehow comes closer to the point than any other line. Some of the points will be above the line, some will be below. So yeah, y hat, and then B0 is B0, B1 type thing. You have an observed value, a predicted value. You have a residual is the actual data point minus what you predicted. So all of these things you're going to be dealing with in the models. All of this stuff we deal with models. Line of best fit. Some of the these are some other formulas here. Some of the squared residuals, least squares. We're going to go through that in the model. I hope that we have it in there because it's one of those things where, every time I do these models, I always look and say, oh, I should have done this, I should have done that. I should have had something else that I should have put in here. I'm hoping that we did the sum of the squares version of things. I hope it's in here. I think it is. Yeah, okay, it's in here. Yeah, so I did throw it in there, which is good. That's line 90 or so. So that's the linear model. So yeah, so again, we looked at the Lowe's data, you know, how well the store did versus the country spending, that type thing. Yeah, then there's a whole discussion. It says the line is social property variation of the data around the model is seen as the residual. It's as small as it can be for any straight line model for these data. The other line has that property. The line minimizes the sum of the square residuals. You might think that finding this least squares line would be difficult. It's not. Legendre, Fourier. These are some big math names that were out there. And again, you don't have it as much at St. Peter's, but that's fine. That's, you know, you can always pick that stuff up on your own. There's another version of this is the straight line equation. See, this is the one based on the data. This is the one that's based on what's predicted, and they're basically the same. But for Lowe's, though, you took all of the home improvement expenditures and you took out the sales of how the store did, and then you computed slope and intercept. And again, unfortunately, we don't have the data I can verify these numbers for you, which really grinds my gears, like the guy from Family Guy would say, grinds my gears. But let's do a little interpretation of everything here. And actually here, we entered some of the numbers, we did some of the predictions. Yeah, and here's the Lowe's data. So yeah, we're going to work on this today. Yeah, this I'm going to knock this column out today, and then regression checking. Okay. Yeah, we're going to hit this well today. Whoops, not this one. That's this one. Okay. So, like I said, I'm going to show you how to get the intercepts and the slopes. But let's interpretation. And I think that the thought. I don't think it was laziness. I think that the thought process with these guys who wrote this book was, let's be able to explain it first, and then we'll go through an exercise of how to generate those numbers. The slope is 0.346. So what does that mean? Okay. Now, you guys recall that 0.346, are units of millions of dollars. So that's really $346,000 is what that is. So what that means is the sales change by $346,000 for every, whatever it is, for every, the sales change for 34 cents for every dollar the nation spends in home improvement. Okay, so a third of the money comes to Home Depot or in this case Lowe's. A third of it is basically spent at the home improvement. And I'm sure you get a statistic guy who argued with me about the way I said that, but that's basically how to interpret this. And what this also means, if the nation doesn't spend anything, that the store is going to earn, 19,000, which not really 19,000, 19 billion. It's going to earn 19 billion. Or lose 19 billion. See, it's a negative. It's going to lose 19 billion. So yeah. Now again, you want to relate, the economic meaning of things, economic meaning of the equation versus just the math. Okay, if this was just a math class, you'd say, oh, the intercept is negative 19,679, then move on to the next problem. We're trying to interpret everything here. And here it says it right here. It says we can expect in a year in which residential improvement spending is $1 million higher to be one in which the low sales. So if there's $1 million spent on home improvements, low sales will be $346,000 higher. That's what that means. And we're going to show you how to compute slope. It's a change in Y with a change in X. You should have had some exposure to slope. It's expressed in Y units versus X units. So if it's dollars to dollars, there's no units. Excuse me, it's just a rate type thing. The response variable changes for one step unit in the predictor. So we'd say the slope is 0.36 million, which is $346,000 per $1 million sales. So 0.346 million versus $1 million. In sales of home improvement in the nation. That's really what that means. And this means you're losing 19 billion to run your store. Theoretically, that's what that means. But does it really mean that? You have to look at the accounting. The statistics are just statistics is applying science to what happens in the world. It's not always going to be 100%. And you've got a job of the economist. It's not to be the most sophisticated statistician out there. The job of the economist is to figure out, is this model really helping us, or is it just a math, academic conversation? And you'll get people who very passionately on the math side of things will defend you know, what they're saying, because that's their currency is how much they can confuse you, and you know, you got to be aware of that. You got to be careful that, you know, that doesn't happen when you're dealing with people, you know, who are doing, you know, this kind of work. Pardon me, folks, for fixing this. I know when I look at the video, sometimes this thing, you know, just I'm very close to the backdrop, you know, and I you know, it's like with Howard Stern. Or one of these days, I'm gonna make my own studio, but for now, I'm just sort of ad-libbing it in sort of an extra room in my house. So anyway, yeah. So you want to look at, you know, national spending, and then, you know, what part of that. And here, if you really look at this equation, this is Lowe's cut of the national expenditure on home improvement, and then subtract out what it costs to run their business. If you want to really interpret that as an economist or an accountant, that's how you would sort of look at that. Okay. But again, does that really match the accounting numbers? And we have to determine that, you know, when you make that comparison. Finding the slope and the intercept. So the slope equation is just the standard deviation of y. Again, you're just going to use these times the correlation. So the ratio of the standard deviations of y to x and times the correlation. Here it says b comma slope. That's either, you know, it's equals b, or slope is what that is. And like I said, we're going to go back to the last thing we'll do is do that problem. Now, as we're rolling down here, though, we have some yeah, we have some stuff here. Yeah, we're here. So I just want to throw this together here. Okay. So slope, fine. Correlation don't have units. You know, it's the standard deviations divide, and r is just a number. All right. So that all cancels. It's just a number. Doesn't have a correlation, but does change the slope to the. So the units of the slopes are ratio 2. Okay. Yeah, you see these now. You can rearrange your sort of equation of a straight line up here. You can rearrange by plugging in the means, and so you have the mean of y minus the slope times the mean of x. That gives you the intercept. That's how you solve for the intercept. So, and again, folks, I apologize. When you see the problem with the numbers, you'll see how all this happens. I'm just, and folks, you should, you know, look, this is our last topic, so by this time you should know how I work. But we're giving you sort of an introduction. We're going to repeat ourselves a couple times, okay, so you see what's going on. What we're saying is Lowe's actual sales, what were the actual sales? Yeah, the actual sales were some of these numbers. Actually, we have two of them here. Yeah. If the actual sales were 12 billion, if the actual sales were 46, type thing. We're looking for residuals. Yeah, you're given this. This is the sales equation. This is how Lowe's sales are impacted based on how the nation spends on home improvement type things. We're just gonna. This is terrible. We're gonna type this in for the time being. 0.346 minus 19,679. Okay. But again, you're going to be computing. This course is you computing these numbers. The nation spent in home improvement, 172 billion. These are just a couple examples. The reason that there's two numbers is there's just a couple examples here. What are we doing here? It says estimated linear model for low sales. Okay. So the nation spent 172,150 million, which is 172 billion, because this is 150 million, this is 172 billion. What are low sales? So you have the equation here, and it says actual sales were this. So yeah, it gives you two sort of choices of sales. So the actual accounting sales were 46 million. 46,927. No, 46. Pardon me, 46 billion. Of course, what am I talking about? 46 million, and then 12,946 is there. All right, we have those are actual sales in this thing. All right, so we have actual home improvement numbers, and then the actual sales of Home Depot. Now, once you have slopes and intercepts, what you can do is you can show up here and say, okay, I'm going to say equals my intercept, lock it, plus my slope, lock it, times home improvement expenditure is 172 billion, and it should be giving me 39 billion, but we spent 46. And actually looking at the residuals here, I don't know why. Yeah, we should have two of these, not just one of these. Yeah. All right, just jut this thing out to the side here, right? Okay, we'll just do it here. So this is the top one, right? The actual. So you take the data minus what you predicted. Yeah, this is just a couple examples, and one overshoots, one undershoots. So the model predicted 39 billion, but the actual sales are 46. So the data did a better job than the prediction by 7 billion. Okay, do I have the data equation? Where is it? I should have it somewhere. But yeah, I'm taking data minus the predicted. I should have that someplace. I'm saying I have it in the problems. But okay, but regardless, that's what we did. You took the data and you subtracted it from what the model predicted. And you have another one of these for 1990 sales. You have 12 billion predicted, or yeah, actual 12 billion actual. And oops, pardon me. This was, yeah, I'm sorry, you got to do that there. This is going to be this, control 1, county, right there. Yeah, same slope and all that stuff. And now the nation spends 100 billion as opposed to 172. So this might be the baseline case. This might be the growth case. So you could see Lowe's was impacted by a lot. It's significant, more than half. A percentage decline of what is it, 25? Yeah, 25 over 40, whatever that is. So certainly more than 50%. That's for sure. So the predicted sales were 15 billion, but the actual were just 12. Okay, again, so looking at what you're having here, you can be above or below the actual numbers. This predicts above. I'm sorry, no, this predicts below, and this predicts above. Yeah, because this predicts 39, you got 46. This predicts 15, you only got 12. Okay, so now what you do is you show up over here, you take your data, right? 12 minus what you predicted, and you can see you're above or below by 7 billion or 2 billion, one way or another. Okay. And like I said, your job is to figure out how to create this equation, create this model, even though it's just linear. That's your job with what we're doing. This is all the stuff that I taught at Rutgers, for years and years and years. So Lowe's did better, and then it did worse. And this just says it in words, what we just did mathematically. Okay. So that's using that equation. And again, you might, depending on how mathematical you are, you might be looking at this going, oh boy, scratch your head saying, oh, De Costanzo, you're not taking it easy. The last couple of weeks, you're still not taking it easy on us with this. But, this is really good stuff. Okay. And if you want to go further, if you want to go further in economics, further in mathematics, further in your knowledge, it's this type of work. Okay. It's just this type of stuff that you're going to need. Yeah, least squares line regression lines, linear model fit by least squares type thing. What do we do here? Yeah, this was the variability of what was happening. Quantitative variable condition, linear condition, and then we're looking for the residual from the regression. So yeah, we're given the standard deviation of x to y is 3 billion. So, and the two residuals are 2.2. Yeah, it gave deviations away. Okay, yeah. So what it did was, yeah, how far it says the two residuals, how far away they're from the mean. Yeah, so the mean of this is. Are we going to go? Are we going 0 with this? So what they're doing is, yeah. So using the 3170, and they're saying it to us here. So, whoops. Sorry. copy. So this is 2.22. So we're hard coding everything here, which I really don't like to do, but 3170. Yeah, see, here's what these guys are saying. Again, when you don't have the data, finding means, all these other kinds of things is a little difficult. If you take 2.2 times the deviation of y, yeah, well, it's got to be y. So 3 billion times 2.2 gives you that residual about 7 billion, and the other one is negative 0.65. All right, right. And this is 0.65. Yeah, so it gives you about those other two, is what it does. It's what they're doing is they're breaking down the residuals. How many standard deviations away are the residuals from the mean, which is 0? Okay, of this. And again, I wish that the textbook had included, the data, so we could have really gone through. Or we're talking about X, we're talking about Y. Obviously, it's got to be Y. But I really wish that the book had given us those data sets. Okay. So another thing you do here, sort of to validate getting those numbers, is you would say equal the first regression divided by 3170. All right, and this equals this divided by 3170. Yeah. See, so I divided. What did I do? I divided the residuals by the standard deviation of the actually the residual itself has a standard deviation. Again, if we had the data, we would be able to show you that. And you're saying how far away are those residuals from the mean, which is 0. Okay. So, but again, we're going to go. Our example is going to show that. Okay. Like this is you're splitting hairs by doing this. You're kind of splitting hairs a little bit by doing. Well, that's fine. Okay, just checking. Yeah, there's a couple more problems here. Yeah, so folks, I apologize for sort of switching gears here a little bit, but there's some sort of in-chapter problems where you're given an equation that says we're going to go back to the lowest thing in a second, but this is sort of in the middle. It says sales per month versus people working. So again, you walk into some of these, on Fifth Avenue. If you shop on Fifth Avenue, you're going to have a personal shopper generally to help you buy something at Tiffany's that's, that you're going to pay thousands of dollars for. Just like most of us would just go to the mall and spend, $250 on clothing at Tiffany's. You could be spending $5,000 on a piece of jewelry that you can barely see, type thing. And there's correlation. So how many people are working, employees, then what are we getting out of that? So all the people that we're hiring, there's some level. We have a diminished set of returns where, okay, we hire one more person, we're not going to be getting as much extra out of that guy as we did with the person that we previously hired. So the equation for that is, so, and in terms of this, if you hired nobody, you would sell whatever, 9.5 or whatever the units are, not 9 million or you'd sell not 9,000. Is it a comma or is it a dot? That's probably a dot there. So yeah, so you'd be selling $9,000 because it's thousand. So 3 more, move the decimal list 3 zeros, 3 places to the right, or multiply that 9.564 by 1,000. And then in terms of the employees, most likely that's a flat number where you're not multiplying by 1,000. But like I said, you got to be careful with this stuff. Again, we weren't given the data set, so when it says sales in month versus number of employees. Now it says number of employees. For all the outlets of a large chain. So is it 122,000 or is it 122? Because it could be either, but it's most likely 120 because they didn't say it was in thousands of employees. So it's probably 122 employees. Because if you think of the stores, how many salespeople are there in some of these stores? Okay, so for each additional employee, monthly sales increased on average by so yeah, so it didn't, you know, you needed more data to make sure your units and all that stuff. But we're just answering the questions. It says what are a typo here. What are the units of the slope? $1,000 per employee. Okay, it's $1,000 per employee. Outland Texas has 10 more employees in the Cincinnati one. So yes, they should be making $1.2 million more because they have 10 more people. So in terms of that slope, what that means is, and again, multiplying by 1,000 to get the sales, you're going to do 122.74 times 1,000, which gives you 102,000. Then 10 more employees, so you're looking at an extra $1 million a month that you could be making. Okay, like I said, you'll get used to the slope. Like I said, we're going to have another video where we talk about all this again. But I just want to go through in a very basic sense, you know, all the Excel stuff. Now we're going back to the Lowe's problem. Oops, not going back to Lowe's, but still with the regression problem. R squared was reported as 71%. So the variation in this model, there's only 71% of the variation of the models that account for in that particular. So about 30% is not accounted for, and so it's not explaining 30% of the variation. You got to compare. It's not just okay if it's over 90. Of course, obviously the highest that's going to be the better. But other models, sort of in the industry type thing, you know, how are other retailers doing with their models? People know that stuff. You know, it might seem like it's you know, top secret, but it's a small world, and people specialize and talk and all these other things, and people, you know, go from one firm to another type thing. But yes, that only means, you know, 7 out of 10 parts of the variation are you know, accounted for in that particular model. Positive correlation because of positive slope, and measure sales in thousands. Yeah, euros, the units wouldn't do anything. Okay, the Europe wouldn't be impacted, but the measure of the slope would be, but the impact, so the R squared wouldn't necessarily be impacted by that. But the measure of the number would be a different number for slope if we used euros. Okay. Yeah, this is another piece of the home improvement model here. We're given a little more information now, and it says the average expenditure nationally is this number, and I'm sure this is, you know, thousands. And again, when you don't have the numbers, it can be a little bit difficult. And the sales, Lowe's average sales, that's a tough thing to use average sales, because, you know, as a business grows, you want that number to be bigger, and as the more it changes, the more it sort of messes up your average. Okay, but this is improvements, this is standard deviation, and then the average sales in 20 years of being in business, which again can be moved one way or another based on how many years that the place has been in business. 14,089.61, which is there. So yeah, average sales 13 billion, deviation by 14. That's a lot when the deviation is bigger than the sales. So you can see with the nation that this is about half of the mean, but here it's actually a little bit bigger. What you do is, and we were given the correlation. So again, we're just entering this, but again, you're going to be computing all this. R squared equals the correlation squared. Okay, that's all this is. So this equals this squared. Okay, so yeah, so 95% of the model. So correlation 90.976. When you square it, it's 95.9 or 95%. So this is just equal to this. And this equals 1 minus the square here, and this equals this thing, which is that. Okay. We have an equation for slope. What is that equation? The equation is, you're going to take the correlation times the ratio of the deviations is what you're going to do. Correlation times parenthesis, this deviation divided by that deviation, which is there. Intercept is the sales minus the mean for the improvements. It starts with the sales, right? It starts with the sales equals sales minus the mean here, and I think times the correlation coefficient. Was it correlation or was it? I think it was a slope. Yeah, pardon. It was a slope. Sorry about that. Right there. It's a slope. There it is. Okay. What happened here? I used A and B is what I did. This thing minus B times that. There we go. Sorry about that. But yeah, the equations are here. The equations are right there. Okay. So we're just based on the mean that you can compute. So now you have a little more information. You're seeing how you're remodeling. Where is it? This thing, right? Not that. Where is it? Yeah, minus 19.346. Yeah, minus again about. It's going to be about those numbers because again, round off error. The data that we used. All those other kinds of things. Okay. So again, this shows you how we sort of derive these equations. The y, you can do it in terms of x. Y hat in terms of x. Similar, right? Minus 20,000 is almost the same as minus 19, whatever it is, right? This is minus 19,679. 0.34 is about the same as 0.3523, the improvement expenditure slope type thing. Okay. And this explains it again. So this is just a repeat. Actually, here the equation is right there. This I don't do the z score too much. Okay, I'd rather just work with the x's and the y's. But if you feel more comfortable working with z-scores, but you have to convert it into z-scores, then you have 2 more columns to deal with. So that's why I don't really do it too much for that. So the regression depends on the units of both x and y. Units are just a slope. Okay, this has no units because the standard deviation is measured in units of the respective variable, so they cancel. Okay. So again, who's the predictor, who's the respondent variable type thing? All this. Okay. All right. We'll pick up in terms of the lecture, because I think we've spoken about a lot of it now. I'm just going to redline this, and I want to get to that problem. So the next video, we're going to pick up here for these last couple sections, and I don't want to rush through this because I can see the video is getting we're going, but these sections are just a little bit of a discussion. So we did half the sections. And let me go back. So here's what the next video is going to be. The next video is going to be the mean age of the cyclist getting run over, and those last 4 sections. But here, let's work out the math for. So at least you've seen how to do this. Right. And here again, you don't have. It's not a big amount of data at all. Okay. I'm sort of here with this, move that over a bit. It's going to be a little cramped. But what are you going to do here? I'll just do it like this and like that. Okay. I have some explanatory response. Now this problem has sort of nothing to do with anything, but this is just the math. Okay, this is just again make sure the conditions are working for you to be able to use this model. So you have ordered pairs 6, 5, 10, 3, 14, 7, 19, 8, 21, 12. All right, that's all the data that you have, and you want to count these. How much how many pieces of data? You have 5 pieces of data. Okay. You're going to clear out the filling. And what you'll do here and here, these 2 places, you'll figure out now again, you have X, you have Y. This is not sales, or we're just going to go through the math. So, but again, so really, if you want to focus, I sort of kept this to the end, but if you really want to focus on something, now's the time. You're going to sum all of this. You're going to count all of this, right? And you're here with this. Okay, so you have your 2 means. You have your X bar and your Y bar. I think what I did was I centered these. Yeah, I think I centered those like that. I was a little bit better with doing that. Okay, that's your data. Okay, that's your data is what that is. Okay. Now, again, all you do is you just how good your math is. Okay, just how good your math is from here on out. Yeah, I didn't graph this because we do have some graphs coming, and we'll do the scatter plots and the residual plots. Well, let's just concentrate on doing the math here. This is x minus x bar. So equals parenthesis. You're going to take the x variable. X bar is here at 4. Control D. And again, I'm a little bit on the surprise side where I'm still seeing people running around with calculators when I'd much rather you work in Excel. The whole point of this course was to work in Excel. If you somehow snuck through 2 classes with me and you really didn't learn how to do anything in Excel, I mean, I don't know what to say to that. I'm speechless. Right? The point was to learn how to make models and format everything and produce these models. Okay, that's the point here. So we're just taking the data value minus the mean, and then what I'm going to do, and actually what I could do, see, if I got rid of AC right there, and I just went down this, and I said shift, I'm saying shift right arrow, then control R, it just locks into the next set of them, and it moves the data over and it moves the mean over. See how that all works? I'll do that one more time. Okay. Here, this is what this. It's your data point minus the mean of x. Lock the row, let the column float, and then obviously do this. Control D, and then shift right arrow, then Control R. It gives you the y bar. It gives you all the y bars. Okay, and next thing you're just going to square that difference. And you're going to do that the whole way down. Control U. Right? It's all this. Okay? Now you're just doing the math now. Okay? You're just doing the math. And all of these things, these are just the next set. Right? This is just the next set squared up. Yeah, and this is just simply, and here, so I don't want to lose, I want to explain that comment in a second. I don't want to lose that comment. This is total sum of squares. So this is the difference in y from the mean, and then you square those. All right, so this is how far away your data is from the average. That's what that is. And then you're going to cross multiply the next two. You're going to cross multiply your difference in x, your difference in y. Underline, copy, paste. All right, you're just summing those. Okay. All right. This is the summation of the product of x. That's this. That's a 72 for this bar, divided by the deviations divided by n minus 1. So actually here, you're just adding up, not adding or counting how many pieces of data that you have. This is your data column. We didn't program this in, but you could just look at how to type that in. Equals count, and then the range of variables, the range of data. Okay, we were fortunate enough where we found, from a sample, we can say equals standard deviation from a sample, and you can just type in, this is for x. All the x, italics, it's a notch smaller. So what you do is you're dividing by n minus 1 instead of n. Okay, so this is for x. Y is the next one over. There's y, and you can't do the residual one yet. But here, you can do the 2 standard deviations, and I'll tell you why we're doing this. You need them to compute the correlation. So you're dividing by the standard deviation of x. Now, just you let Excel do it right here. Well, let's do it ourselves. Okay, let's do it ourselves. So equals SQRT. The sum of the squares of x are there, divided by parenthesis 5 minus 1. And you'll do it again. It's just the y's now. And this should have been blocked. Okay. See how they're almost the same? So actually, these are exactly the same. Because it's a sample. If you divide by m, so this form, we just showed it in Excel how they got the 6.2 to 3.39. I think that's valuable to understand how that works. Okay, I think that's pretty valuable. You can't do the residual yet because you need the correlations. Now with the correlations, it's a sum of the product of the x and the differences in x and the y relative to the averages. So this is going to be equal to this 72 divided by parenthesis n minus 1 times the standard deviation of x times the standard deviation of y, parenthesis, yeah. And there you go, 0.8554. Right, we did it like that. Yeah, I did it using that one, and then we did it another way. Yeah, I flip-flopped them. So I did it twice. The other version of it, without using the deviations, you could just say equal the sum of the x minus x bar, y minus y bar, divided by parenthesis SQRT, parenthesis, the summation of x squared times the summation of y squared. And I think that's it. Oh, was there another? Yeah, there's another one. Excellent. Okay, did it. Yeah, see, 0.554. Okay. Now, folks, I apologize. Now, once you have the correlations, you can come down here, and the slope is the correlation times the ratio of the deviations, which is just this. And the intercept is just simply y bar minus slope times x bar. Okay, so that's like a 0.45. And when they're close like that, you got to be careful that you don't confuse them. But here's the equation. Y hat equals this. I could have had another equation, sort of the usual equation that we had here, and maybe I'll just jam it in there real quickly. Where is it? Where is it? 8133. Copy. X and the intercept is 0, 4, 5, 4, 5. Another way to do it is this. Put it sort of right next to it. Okay. And actually another sort of a third way, and again, let's spend a little bit of time doing this Excel stuff, because what we need to do is now we're going to insert this equation into the predicted part here. Actually, what I want to do, I want to copy this. The other thing we can do is equals this concatenation function. So this is quotes This is an equal quotes, comma. This is the intercept, comma, quotes, plus quotes, comma, slope, x, quotes. See? It gave us that. So as these things change, it'll work in there. But here's the thing, though. We want this to be, and here, let me do this. I don't want Adobe. I don't want that. I want the view, home. If you just hit F1, yeah, this thing needed to log on. Yeah, if you want to make the numbers dates or put decimal places after them or something, you use this. So see, we use concatenate, but I want to say text parenthesis the number and then another column, and then it's going to say quotes $, decimal. Now I forget the zero and the $. I think the zero and the number symbol. I think you should put the zero should be the end type thing. Let's see if it makes a difference. And it doesn't seem to make a difference. See how it? So again, you can see this, folks. Let me tell you something. Word processors long ago sort of worked like this, believe it or not. Okay, so yeah, to sit this, I can't use Word. I can't use something. Believe me, you guys don't realize how tough it was to do this stuff, long ago. So oops, and something. I see what wrong here. This needed to be 0, and this needed to be 0. There it is. And now we have zeros in there. But you can see what happens though. And actually, this is why. Yeah, I guess we're sort of stuck writing it that way. So you use various versions but you use the Excel help thing as much as possible. I think it's under file. Yeah, it's under file. I was looking for it. Yeah, it's under file. So okay, I'm not done yet though. Okay, so we're not finished yet. But yeah. So again, if you want to get a little experience list summer, I taught this a little bit more than I taught it now. But that's a nice thing to be able to do. So as your slopes change, you have to rewrite. You have to think to retype the equation. So I showed you how to do it using sort of an image, and then you have this. Just the standard way to type it, and then you have a little more dynamic version of it. Okay, but of the three of these, you're going to come up to predicted. You're going to say equals. You're going to say intercept, lock it, right, with the $signs, plus slope, lock it, and then times x. Yeah, 3.2, 6, and then go all the way. Okay, so that now this is your predicted, column here. Actually, let me make this very light gray, and this is your data column. Okay, so you want to compare those two: 5, 3.6, 3, 5, 10. Okay, I mean they're in the neighborhood, but they're sort of moving all over the place. The residual of this thing is equal to parenthesis the data point minus the predicted. And again, the equations up here tell you what to do. And you're going to go down the whole story. Okay. Then you're going to take the average of this thing. Right, you take the average, this is 0. And then you're going to square all that. Right? You're gonna, oh, that's right. I don't know why that happens. This should just be like 3 or 2. I don't know why that. I apologize when that happens. So that's the square of your residual. And you're going to go all the way down. Right? You're going to underline this thing. And then you're going to say equal sum. All right, 12.34. And what does this thing say it is? This is the sum, right, sum of the squared errors. And this is the sum of the total sum of the squares. You're going to use that here. You're going to say equals 1 minus SSE divided by SST. Right, and there's your, all right, there's our check, as we like to call it. Okay. So that's how much, so about 73% of the variation is explained in the model. So this equals, you know, my correlation squared. Again, I apologize when that happens. And this has got to be, you know, 2. I don't know why it goes to 15 like that. Okay. Or, you know, more, whatever. We could do 4 decimal places with that. Okay, and this is equal 1 minus r squared, which is that, and that equals the other part that's not accounted for. Folks, when you look at this, see these little red sort of triangles? If you hover over it, it tells you the variance not accounted for in the model, variance accounted for in the model, what all this stuff means. Okay, and now that you have this, now you can start doing standard deviations. This is E. There's E. Yeah, 1.76. And then if you do it, is the sum of the squared, which are right there. And this is that 5 that should be locked. 1.76. It should be exact. Yeah, why isn't this exact? We did -2. You see, -1 is what it gives you. This has got to be -2. There it is. There's a couple more degrees of freedom. All right, a couple variables and all that other stuff. Right, you have 2 variables. That's why. Okay. But yes, like I said, so I'm not going to cram this in another video because we've been going a good hour right now at least. So so yeah, so there you go. Okay, so you saw this. You know, yeah, I'll post this. Okay, and actually what I'll do is I'll put a big red blot there. So we have 2 more, we have a couple more sections to do and another model, and we'll make the scatter plots and we'll do all that. Okay, but we'll do this next time. We'll do this next time. More discussions, and it's good to hear, you know, correlations, weak, moderate, strong, and form, you know, direction, all that stuff, strength, and we'll keep having that conversation. Okay. Okay, folks. Again, always, you know, it's a tremendous pleasure to get online with you, and I'm glad we resolved our technical issues with the choppiness. I apologize for a number of those videos that were choppy, but now we're using Google Meet, and it seems to be working a little bit better, which is good. I appreciate that. But yeah, please, there's 2-3 weeks to go, you know, 2.5 weeks to go in the course. But again, you shouldn't have, if you're one of those people who waited, and now you're trying to watch these videos and do everything at once, I think that's really, you shouldn't work like that. You know, you really shouldn't work like that. I've said it a number of times. I don't know what else I can do. So, all right, folks. But yeah, we're good, and we'll see you next time.